So the following design steps are recommended when we design solar active technologies. First, we should define the required data about building and climate. The climate, as we discussed before, has a very high importance on the design because it will affect the selection of resistance of the envelope, the level of insulation, the orientation of the building, etc. Then we should look if it's possible to obtain enough collector area, because sometimes you know that when we have buildings, we might have several floors and a limited roof area. And in general, we place the collectors on the roof. That's why, because of this limitation, currently we are trying to develop, if you want, the facades of collectors in a way to not, if you want, compromise the aesthetic of the building. So we are trying to suggest beautiful facades that can allow to collect a high amount of solar energy. So this can overcome the constraint of the area. But of course, we have the concern with the orientation and how it can trap the, the solar energy, because on the roof you can play more with the orientation of the panels. So of course, it has certain considerations that should be taken into account to be implemented. Even here, we can place some movable panels that can change in orientation. So we can determine if there are restrictions on inlet temperature from ventilation system. Plus, before this, we should go over the required ventilation rate through the solar air collector. So depending on your application, what is the amount of heat required? Then you need to determine the mass flow rate, because let's say you want, if you have a lot of occupants, you need to circulate a larger flow rate of water in order to satisfy the needs of water. Let's say if you have space heating for a bigger area, you need a larger m dot, etc. So depending on the application, you should select what is the difference of temperature delta T you want to create, what is the mass flow rate of the fluid you want to circulate. Okay, because you know that the heat that is taken by this fluid will be equal to m dot Cp delta T. So you need to do a preliminary design to decide on the mass flow rate, and accordingly, when you are designing active technologies, this mass flow rate will require a certain pumping device to circulate it. So you should size the pump and determine its specification. You should also determine if there are any restriction on inlet temperature from ventilation system. So you might have a certain range of delta T to work with. You should investigate if it's appropriate to include a storage system or not, because including a storage system will add to the initial cost. So if you don't have already in excess, if you study your system and you don't have excess of energy, you don't put a storage system, because in this case you will put an initial cost and you will not get any benefit. On the other hand, if you have days where you have excess of energy and this excess is worse to store, okay, because it will reduce the energy bill, then you can go for it. Okay. Now you should select also if you want a control strategy for your system. Sometimes you need, as we have seen before, you have a valve that can circulate in different ways water. So depending on the needs, this can be operated by a control system. Of course, it is used in general. It's based on sensors that can measure temperatures. Let's say of water in the reservoir of water to shower. It can have a sensor. Once the temperature drop below a certain required temperature, then this will open. The valve will open, etc. You should define also what is the type of solar collectors that is convenient for your application, what is the number of collectors to use, what is the total area needed. You should investigate if the system can be used for other purposes. And sometimes if you have, let's say, excess of heat for domestic hot water, you can say, why to not implement also a floor heating system? Uh, you can you should decide on the final collector area. You should size the ducts because you need a distribution system. You have ducting, so you should size the ducting. You should select appropriate fan or appropriate pump. You should choose diffusers, etc. Now, other very important active technology is photovoltaic PV systems. And already we discussed in class how this technology involved in a very fast way. Because at the beginning it was very limited because of the temperature limit and decrease of efficiency, and we're able to overcome this with advancement of technology and engineering ideas. So when the sunlight strikes a photovoltaic cell, electrons in a semiconductor material are freed from their atomic orbits and flow in a single direction. This creates direct current electricity, which can be used immediately, converted to alternating current, or stored in a battery. PV cells normally have a lifespan of at least 20 to 25 years. However, they usually last longer if frequent overheating is avoided. So a temperature in excess of 70 degrees should be prevented. PV systems can be used as a building sole electricity supply or with other sources such as a generator or a grid connection. So from here also the importance of smart grids and how we can connect PV systems on a large scale to benefit from excess of energy in case we have it. And in case we have a lack, we can have backup from the grid. Now, in photovoltaic PV systems, we have a semiconductor material that converts solar energy directly into electricity. The autonomous PV systems are used with battery storage, so you can, if the supply is limited, or if you have, let's say, you design enough number of PV cells that you use, you can be completely independent. So you don't need to have electricity from other sources. And in case you need other sources, you can have a backup system. But in general, it can work as an autonomous system whenever you have a battery storage, because during the day it will store the excess in the battery and it will deliver it for you during the night. So to have a completely independent system, just you have to select the appropriate battery size and the appropriate number of PV cells. In case you find the investment high, you can combine with another backup system. Hybrid PV systems have at least one additional electricity source. So in case you have a space limitation or you have a cost limitation, you can implement PV system with another electricity source, such as fuel-fired generator or a wind turbine. Grid-connected PV systems will cancel out the need for on-site generators and batteries and eliminate the problem of intermittent solar energy. We started to do this in Lebanon in some regions. We are trying to connect PV system on the whole region, and in this way we can avoid the need for batteries, because whenever, let's say, you can distribute the energy in a more efficient way whenever you have it in excess. So based on annual growth rates of 20%, the break-even point for competing with bulk electricity generation was calculated to be between 2020 and 2030. This was based on lowest production cost, but does not consider technological advancement or the advantage of reduction greenhouse gas production. So we'll see how to perform. In this course, we'll develop tools to perform economical analysis that can give us idea about, let's say, for a certain technology, when can it compete with other resources, and plus how we can account for, let's say, such issues like technological advancement and environmental positive effects. So here is a figure showing solar active technologies using the photovoltaic PV systems. So as you can see, you can integrate it to the roof, you can integrate it to the facade as we discussed, and this will give you a large exposed area. Some information about this important technology. On the 24th of September 2013, the German Institute for Solar Energy Systems announced that they have achieved a new world record for the conversion of sunlight into electricity using a new solar cell structure with 4 solar subcells. surpassing competition after only over 3 years of research and entering the roadmap at a world-class level. A new record efficiency of 44.7% was measured at a concentration of 297 tons. If you are interested more into this technology, you can go through this link for more information, and you can include it in your project in case you are tackling solar energy. Now, as we know, in many sources, for example, in PV case, we have overheating. So we have loss of energy in form of heat. So if we can benefit from this lost heat in an efficient way, then we can increase a lot the efficiency of the system. This is the principle of heat recovery that we already discussed together before. So heat recovery consists of using the unused heat or rejected heat from any hot process. It can be from power generation, from boiler, from PV cells, etc. So we can do heat recovery at the condenser level in case we have a boiler. We can consider heat recovery from exhaust gas heat exchanger in case we have, let's say, in case of thermal combustion engines. And in case of PV, we can have a heat exchanger circulating fluid at the back of PV panels in order to take the heat that is generated. And here, if we do this, we can reach very large efficiencies, okay? Because we can use, if you want energy, okay, the whole amount of energy needed. Yani example, you know that in what do they mean by we can reach efficiency larger than 100%? You know that, let's say, in a system, if you put from thermodynamics, if you put certain amount of work, okay, let's say in a refrigeration system, you can force heat to go from a relatively cool place to a hot place, okay? Now, in case the heat that you are rejecting here, you use it, okay? So in case you use rejected heat, then you can have an efficiency that is very high, okay? We talk about also COP here, coefficient of performance, because what is W for a closed system? Let's say W is the difference between a Qn minus Q out. If you do an energy balance for your system, okay, you are forcing energy to go from one level to the other, okay, which cannot be done in a natural way. So if you study your system, you can do a balance of energy on your system, okay, and you say that I have here an inlet and here an inlet, okay, so these two energies are coming inside, and I have an outlet flux. So let's say it's a Q out, because W plus Qn will give you Q out, okay? So W is the difference between Q out and Qn. Now, in case, and if you want to study, let's say, the efficiency of this system, okay, you will say it depends on the application. Let's say it's you want to cool a space. If you want to cool a space, what will happen? You need to put your room from this side, okay? You put your room from this side because you want to extract heat from the room and you want to reject this heat to the outdoor environment, okay? And because you are putting work on your system, you can extract heat from a relatively lower temperature, which is inside of your space. An example, during summer, let's say inside you have 27 degrees and outside you have 35 degrees. When you operate your ventilation system, you are able to supply you by just putting electricity, consuming electricity, and this electricity will be converted to a work in the cycle of refrigeration. This work, when you put it, I will not go over details of thermodynamics, but just the idea. When you put this work, you will force heat to move from the inner space, which is at 27, and you reject heat from the fluid that is circulating in your HVAC system to the outer environment. Okay, and if you want to calculate the COP, which we call coefficient of performance or energy efficiency, what you do is you put, what is the useful heat I did here? I was able to extract Qn. So this is the useful thing I did. So I divide the Qn by my input, which is the power, by W. Okay. And here your COP can be smaller or larger than 1. It depends. Okay, it depends on the values of Qn, Qout, and W. Okay, so what you can say here, how can I profit to the maximum from my energy? To profit from the maximum, what I can do is I should use Q out also. Okay, Q out is larger than W. Okay, while Qn can be smaller or larger, it depends. But Q out, of course, is larger because Q out is W plus Qn, and I am not taking advantage of Q out. Okay, because it's released to the surrounding. If I want to get advantage from Q out, I need to use it somewhere else. So let's say this heat is used, let's say, by circulating a heat exchanger. Yani the exhaust air, okay, can pass through a heat exchanger, and heat then can be transferred to a circulating fluid that can be used for any heating application. Then the COP, instead of being a Qn only, because here you put the useful heat that you have, instead of being just Qn, then your efficiency will be Qn plus Q out. Of course, maybe you will not be able to recover 100% of it. So if you just can recover a certain percentage, so let's say times a certain percentage, larger this percentage, larger will be the heat recovery over W. You can reach then very large efficiencies, larger than 100%. Okay, so heat recovery is very important because it will allow you to use waste energy in a useful form, and therefore you can reduce a lot your energy consumption. And you can also use heat recovery, let's say, from gray water. So drain water, it's called drain water heat recovery from the shower, etc. So the heat recovery concept is very important because it can lead to a very high increase in the efficiency of a system, and this is very important on the economical level. Any question on this? Okay, so we are done for today. Hopefully see you next time in the CFD lab session. Bye bye.
Thank you, doctor. Have a great
You too. Bye bye.
weekend.
Bye.
Bye.